Okay, so we will talk about really a cool data structure which is called Emde Boas data structure. So, this is to deal with the problem what is called fixed universe successor problem. Fixed universe successor problem. So, basically we need to maintain a dynamic set S, and this S, the elements are coming from a universe which is fixed. We know the universe. So, S is a subset of the universe. Universe are typically u minus 1. So, the size of the universe is basically small u. So, we know the elements, they are basically from 0 to u minus 1, and the elements are coming from this. So, this set is dynamic. So, that means we should able to insert a element. So, we should able to perform this operation, dynamic operation, insert an element x which is in u, but not in S, and we should able to delete an element from S, and we should able to find the successor of an element in U. So, that means we want to report the element after x in S. So, suppose our S is like this, S is say 3, 4, 6, 9. Suppose this is our S at some point of time. Okay. So, now successor, say suppose successor of, we want to find out successor of 3. So, successor of 3 is basically the next element in S, 4. Now, we can also query this successor of say 5 or successor of say 7. 7 is not in S. So, it is not necessarily that successor query will be on the element which is only in S, it is any element in U. So, this is basically 9. So, this is the after 7 what is the next element in S, this is the successor. Similarly, we can have a predecessor. So, before that what is the previous element in S. So, this is the problem. So, for this problem we need to have we want to design a data structure to solve this problem. So, can we suggest some data structure for this? So, maybe we can think of say linked list. So, linked list, suppose we maintain a linked list for this S. So, once we have a element, so we have a top and we just suppose there are n elements. So, this is the list and last one is the null, and there are elements. And so, now if we use linked list, then what is the time for insert? If you want to insert an element x which is not in S. So, insert means we may have to insert here, or we may have sorted this. So, insert will take linear time. For delete also, if it is not sorted, we need to find the element. So, that is also linear time. Now, the main thing is the successor query. So, how much time it will take for successor of. So, for successor, even if it is sorted, we do not know, I mean we may not start from that point. So, that means for successor again we need to scan the list to find out the next element. So, successor will take again linear time. So, we want to do something better than this. So, can you think about some tree like binary search tree or balanced binary search tree, balanced BST, okay. So, we have a n element and we maintain a BST. I mean we can have a red black tree which is balanced, we know. So, we can maintain a balanced binary search tree, okay, like this. Okay. So, suppose this is a tree and now suppose we want to find out the successor for this. So, successor for this is basically this guy. So, we have to go to the from this node to the root. So, the time for the successor is log n base 2. Okay. So, this is if we use the tree, especially the balanced binary search tree. Now, we want to do something better than this. Actually, we want to do this in order of log u time. So, that is our target. We want to do this successor query or insertion in the order of log u. So, how we can get the time? This is log u. You can just write this log of u. So, where from we can get this time log of u? I mean any situation where our time complexity will be log of u. Any idea where from we can get this time? So, any recurrence you think which can give this solution this? Suppose we have a recurrence like this. See log n we can get when we have a tree of size n and we are searching something there, I mean binary search. Suppose we have log u number of elements and we are doing the binary search, then it can give us log of u, log u. Now, we want to know what recurrence can give us this solution. So, if we have this recurrence this, so if we have this recurrence, then the solution will give us log of log u. Why? Because if we just put this u as a log u, then this will be log of u by 2 and then by master method this is basically log of log u. So, we want to get this type of recurrence for this problem. So, this is the this is our goal to achieve this recurrence, so that we can get the solution as log of log u. So, now the question is how we can get that. So, this is the idea of Emde Boas and he has designed this data structure. So, you start with the array, this is the first step, array, or this is called bit vector. This is simply an array. Okay, suppose our u is say small u is say 16 and our u is say 0, 1 to 15. And we have say number s is like this, we have taken say 3, 5, 6, 9. Suppose at some point of time this is our number. So, what we do? We just maintain an array of size u. So, this is basically u array. So, it is starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So, this is the array. Now, if a element is present, we will put a 1 there, otherwise we put a 0. So, 3 is present 1, 1, 1, 1. So, rest are 0. So, this is a really cool data structure, very simple data structure. This is just a called bit vector, switch on off. If that room is on, light on, that means that element is present. Okay. So, this is the way, this is the array we use for this. Now, to insert an element, if you want to insert x, okay, suppose we want to insert say 8. So, what we do? We will go to the array 8 and we will put it 1, that is it. So, we will go here, it was 0. So, now it is 1 if 8 has to be insert. So, this is the insert operation, and delete is also same. If we want to delete say 5. So, what we do? We go to the U5 and we make it 0, switch on off. So, this we make it 0 like this. Okay. So, how much time we are spending here for insert and deletion? For insert and deletion, it is just a constant time, we are just bit on off like this. So, now the what about the successor? What about the successor query? Suppose you want to find the successor for say 0 or 1. So, successor query, for successor query maybe we have to scan this array. So, it will take basically order of u time, okay. But we want to do it in better way. So, what we do? We divide this array into blocks. This is 16. So, we will divide this array into this many blocks and each of size root u. The block size is root u. So, that we will do. So, how to do that? So, suppose this is our number. So, 3, 5, 6 and we have 9. Okay. So, we divide. So, u is 16. So, root u is 4. So, we divide into 4 bits. So, here, 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 here. So, we divide this into 4 bits. So, this is the first 4 bit, this is the second 4 bit, these are also called widget or the blocks. Okay, this is the first widget, we denote at W0, this is W1, W2 and then we have W3. So, we have basically 4 widget and this is basically W00, W01 like this, W03 like this. Okay. And the numbers we have a 3 over here and we have 5 and 6, 0, 0, 0, 0, 0 and we have 9 over here. So, sorry, 9 is here 0, 0, 0 and all are 0. So, this is the way we represent as a blocks. So, this is the u is 4. So, this is how many blocks we have? We have root u blocks and each block size is root u. Okay. So, now how we can insert an element? Suppose we want to insert say 7. So, x equal to 7. So, 7 in how we represent 7 in binary? So, 7 is basically 0, 1. So, this is basically 4, 1, 1. So, 4, 2, 1. So, 7. So, this we denote by high of x and this we denote by low of x. Okay. So, high of x will give us the block number. So, basically we will go to W of high of x, this will give us the block number and this low of x will give us the position in that block. So, this is basically we will make it 1. This is the insertion. So, insertion is basically we will go to that particular block or widget w of high of x. So, in this case this high of x is basically 2. So, we go to this so high of x is high of x basically 0 1. So, it is 1. So, we go to w 1 and then we go to the in that widget we go to the low of x position. Low of x is basically 3. So, we go to the here. So, this is basically we make it 1. So, this is the insertion, and similarly to delete we will do the same thing. So, we will go to the this x we make it into 2 part, high of x into root u. So, this is x can be written as this plus low of x. So, this is denoting the which block it is belonging, and this is the in that block what is the position. So, we will go to that particular field. So, w of high of x and then low of x we will make it to 0 for deletion. So, how much time we are spending there? It is just a constant time. Now, what about the successor? What about the successor query? Okay. Now, suppose we have this situation, suppose we have here it is 0 and suppose we have here it is 1. So, S is now, so 3, then we have 5, 6, 7 and then this is 15. Suppose S is like this. Okay. Now, suppose we want to find out the successor of say 7, x is 7. Okay. So, what we will do? So, we first make it into 2 part, high of x and low of x. So, we go to that w of high of x, that particular widget, and then we find out the successor in that widget. If there is, if this is the last element, so no successor exists here. So, what we do? Then we go for the next block where we can find out the widget, but this block is empty. So, but we have to check it. There is no way we can because we do not know whether this is empty or non-empty. Then we cannot find here, then we will go for here, then this is the. So, how we can augment the data structure so that we will not go into this block. So, for that what we do, this is just a simple augmentation in data structure. We will put a extra bit of information which is non-empty. So, this is the non-empty bit. So, what we do? If there is a 1, we will put a 1, otherwise if there is no 1, we will put a 0 and we will put a 1. So, the algo is now, so what we are doing, suppose we are finding the successor of x. So, what we do? We look into look for successor of x within the widget or within the widget w of high of x. We will look at within the widget w of high of x and starting from low of x. So, this is the first step. Okay. Suppose we want to find the successor of say 1, successor of 1 or 2. So, what is the high of x? High of x is 0 and low of x is basically 0 1. So, low, so this is basically 0 0 1 0. So, low of x is 2. So, we will start from this widget and we will start from this low of x. After that, we will find the next one, we will find the successor in this block. Suppose if this is 0, then we have to look at the next non-empty block. If successor found, then we successor found, then we return it. Okay. Otherwise, we will just look at the else, look at the smallest I greater than high of x, for which W I is this widget is non-empty. Okay. So, that means we will, if we are not finding here, we will look at the next widget where we have a non-empty. So, this is non-empty. So, we will look at here. So, that is the idea. So, this is 2 and then in 3 what we do? Then we find the smallest element in W I. So, suppose we know this is the non-empty. So, we will return the smallest element. So, this is has 1. So, we will return this. So, this is the code. So, this is basically what is the time complexity for this. So, we are looking for a successor over here. So, this is size of this is root u. So, this is of theta of root u, and we are again we are looking for a non-empty widget. So, that means this is also a successor problem. So, we are after that we are looking for what is the next one. So, that is also, so this is also order of root u, and then again in that block we are looking for a successor starting from, say this is a successor starting from minus infinity to this. Okay. So, this time is basically order of root u, but we want this time is log u. So, for that we need to achieve this recurrence T u is equal to T root u plus theta of 1. So, how we can achieve the recurrence? So, we need to have a recursive call for this algo. So, can you define a recursive call for this? So, what is the recursive version of this algo? So, can you have a recursive call for this? Yeah. So, this is basically successor of say in the W of h of x in this array after low of x. So, this is a successor call, and here also this is also successor call where in the that non-empty array, So, this is basically successor call of yeah. So, let me write again, successor on the non-empty array after this h of x. So, this is also successor call, and the last ones, once we know this is non-empty. So, for this is non-empty. Now, here what we are looking for? We are looking for the first non-zero element. So, that is basically also a successor call, successor of sort of minus infinity in that widget W of I. Okay. So, basically this is a 3 successor call. So, the recurrence will be T u is equal to 3 T root u plus theta of 1. but this will not give us the log u. So, we need to reduce this successor call to 1. There are 3 successor calls. So, how we can reduce the successor call to 1? Only one successor call. Now, see, if we cannot find here, then if we can find the successor here, then we are not going to these 2 level. Okay. So, and if we are not finding here, then we are going for these 2 call. So, how we can reduce this to 1 call? So, idea is we want to do the more augmentation on the data structure. So, along with the non-empty bit, we want to store the maximum and the minimum, maximum position up to where this 1 exists. So, if this is the array, so we have this and this is the non-empty bit. Along with this, we have a maximum max bit. Max bit means if this is say 1, 0, 1. So, that means this max bit will be 3 over here. Okay. So, this is the maximum position where 1 is. So, what is the benefit of this? So, for this, if we know the maximum and if we our low of x is greater than maximum, then we know that there is nobody here which is a successor. So, we will not call this successor call for the first case, then we will go for successor call over here in this non-empty bit. Okay. Now, if we know the maximum is this maximum bit is greater than low of x, then we will do the only one successor call there, because we know there is a successor. Okay. But if there is no successor there, then we have to look at the first non-empty bit. Suppose this is 1 and then suppose 1, 0, 1. Now, here we need to get the successor. So, how we can get that? So, we will just do further augmentation, we will put minimum also, because we already made a successor call. So, we will put the minimum. So, minimum means this minimum is 1, this minimum is also 1, that means where the, so this will give us the successor of x. So, we will just look at this minimum and we will return that. So, basically we are doing only one successor call. If low of x is less than maximum, then we are looking for the successor in that block, that is one call. If not, then we are taking a call to get the successor in this, I mean non-empty element in this, then we going to the particular widget and then we are returning the that particular minimum element over here. So, only one successor call we are doing in any case. So, that is the reason our recurrence is +1. So, this will give us the solution log u. So, this is the idea of Emde Boas. So, this is really a cool data structure, and we are by this augmentation we are getting this time complexity. Okay, thank you.